This is slide number 45 and I am your presenter Asloob Mudassar. Fresnel diffraction by a sinusoidal amplitude grating. Look at the figure. There are two planes, zeta eta plane and the xy plane. Both planes are parallel to each other and separated by a distance capital Z. And on the eta zeta plane we have the grating. The grating lines are running parallel to the eta axis, and they are separated from each other along the zeta axis. The profile of the grating, that is the amplitude transmission of the grating, is known. We shall illuminate this grating with a unit amplitude normal incident plane wave, and the field after the grating will be known, and that will be used to calculate the field at the point P naught, which is lying on the xy plane. So this is actually the problem that we have to solve. Now consider a thin sinusoidal amplitude grating of infinite extent lying on the zeta eta plane with grating lines running parallel to the eta axis. The grating lines are separated by a distance capital L along the zeta axis, and the spatial frequency of the grating will thus be equal to the reciprocal of the separation, that is 1 over L. So the true grating is shown in the figure. So this is the sinusoidal grating, and you know that you can look at the profile of the sinusoidal grating along the zeta axis, and the lines are running along the eta axis. Due to this grating structure, we want to determine the field at the point of observation P naught located at a distance capital Z from the input plane. So in equation number 50 we have the amplitude transmission of the grating. So Ta as a function of zeta eta is equal to 1 plus m into cos of 2 pi into 1 over L into zeta. So this profile will run for all values of eta. So you see that here you have 1 over L, which stands for the spatial frequency of the grating. So this is the amplitude transmission as shown in equation number 50. The true sinusoidal grating representing Ta of zeta eta is also shown. So this is the true representation of the grating, you know. The one-dimensional amplitude transmittance function Ta of zeta of the grating is shown for 3 different values of m. So we are taking the one dimensional of this quantity. Again it is in the one dimensional, and you know that the subscript of this one shows that it runs for all values of eta. So removing this, that it runs for all value of eta. So this is the profile, one dimensional profile, and we are plotting this one dimensional profile in this figure. So you can see that we have used 3 values of m. M is equal to 0.4. In the middle we have used m is equal to 0.6, and on the right hand side we have used m is equal to 1.0. We have plotted zeta coordinate along the horizontal direction and the amplitude transmittance along the one dimensional along the vertical direction. So you see that look at the figure, in the figure where we have m is equal to 0.4. Look at the visibility. And when we have m is equal to 0.6, the visibility will improve, which is indicated by the 2 arrows. That is from the minimum of the signal to the maximum of the signal will give you the visibility. And when m is equal to 1, then you know that the minimum touches the 0 axis, and then the maximum value is equal to 2. So the visibility is 1 over here. So in principle, m value actually giving you the visibility of the fringes. The parameter m controls the visibility or the contrast of the grating function, which is maximum for m is equal to 1. So the visibility cannot exceed m. So the maximum value for m is equal to 1. The visibility V or the contrast of such a function is defined as given below. So this is the visibility. V is equal to I max minus I minimum over I max plus I minimum. So if we apply this formula of the calculation of visibility to the last figure over here for m is equal to 1, you see that here the minimum intensity is 0, the maximum intensity is equal to 2. So if you put 2 value, that is the maximum is 2, the minimum is 0. So 2 minus 0 over 2 plus 0 become equals to 2 over 2 is equal to 1. So you see that the visibility is equal to 1. So similarly, for other values of m, you can determine the visibility from the numbers that you have. For example, for the middle one, the lower value is 0.4, the maximum value is 1.6, and if you put these values for the minimum equal to 0.4, maximum equal to 1.6 for the middle figure, you will get m is equal equal to 0.6 from the visibility formula given in equation number 51. So let's assume that the thin infinite sized grating, that is on the figure, the previous figure, is illuminated normally by a unit amplitude monochromatic plane wave. So you see that here we are assuming that we are illuminating this grating with a unit amplitude normally incident plane wave. And you know that when we use a unit amplitude, it means that the magnitude of that wave is 1, and normally incident mean that the plane has a constant phase value over there. And when the plane has a constant value, it means the constant phase, it means that we can drop that constant phase value over here. So the field just after the grating is represented by u of zeta eta is equal to 1 plus m into cos of 2 pi into 1 over L into zeta. So you see that this is the same as the transmission amplitude of the grating, because the transmission amplitude of the grating was multiplied with 1, which is the amplitude of the input plane wave, and was also multiplied by some constant phase factor. And you see that for a plane wave, when the phase factor is constant, we can drop the phase factor, constant phase factor. So that's why we have dropped 1 over here. We have also not shown the constant phase factor due to the plane wave, and we have written the field just after the grating, which is equal to this one as shown in equation number 52. Assuming that the field u of zeta eta is known. So the field in equation 52 is known. We want to determine the field u of x comma y at the point P naught. Fresnel diffraction formula given in equation number 9 or equation number 33 cannot be used because both these formulas involve integrals over infinite extent in zeta and eta coordinates, and in our case u of zeta eta depends only on zeta, and thus the integral in the eta cannot be evaluated. Thus the two forms cannot be used. Because the integral involving eta have infinite dimensions, we cannot solve that integral. So the possible solutions through equation number 9 and equation number 33 is not possible. So instead we are using the Fresnel transfer function approach given in equation number 20, given in equation number 22 will be used to find u of x comma y. Omitting the constant phase term over there, the Fresnel transfer function is reproduced over here in equation number 53. So capital K at Fourier frequencies fx comma fy and subscripted as Fresnel is equal to e to the power minus iota pi lambda z, and within the parentheses we have fx square plus fy square. So you see that this is the transfer function of the Fresnel formula, which we shall be using in order to calculate the field at the output plane. And the formula to calculate the field u of x comma y at the output plane is given by this relationship. Look at this relationship. You see that we have taken the inverse Fourier transform. On the right hand side, the product of two quantities. One is the Fourier transform of the input field multiplied by the transfer function multiplied by the Fresnel transfer function. So you see that if you multiply the Fourier transform of the input field with the transfer function of the Fresnel formula and then take the inverse Fourier transform of this product, you will ultimately get the quantity on the left hand side, which is the field at point x comma y. So it means that in order to use equation number 54, we have to determine two parameters. One is the Fourier transform of the field of the input field, and you know that this capital K is already known to us as given in equation number 53, and then you know that we have to take the product of these two quantities, and at the end we are going to take the inverse Fourier transform. So you see that the Fourier transform of the input field is shown in equation number 55. So in the first line we have taken the Fourier transform of 1 and then plus m times the Fourier transform of the cosine function. So the Fourier operator, you know that it is, depends upon the zeta as a function of zeta. It will operate on the zeta coordinates. So you see that the Fourier transform of 1 is delta function is a point, will give you a delta function. So delta of fx comma y fy is the Fourier transform of 1, and then the 4m multiplied by. So you see that we can convert cosine into two functions, e to the power iota 2 pi 1 over L into zeta plus e to the power minus iota 2 pi 1 over L into zeta. That is, we can use the exponential form of the cosine functions, and then you know that when we shall operate the operator on the two exponential forms, we shall get two delta functions. One delta function is has an argument fx minus 1 over L comma fy, and the other delta function has an argument fx plus 1 over L comma fy. So these are the two delta functions. So you see that the whole Fourier transform of the input field contains three delta functions. One as a delta of fx comma fy, the other one is a delta of fx minus 1 over L comma fy, the third one is a delta of fx plus 1 over L comma fy. So if you notice that the first delta function will be non-zero only when fx is equal to 0, fy is equal to 0. The second delta function will be non-zero only when fx is equal to 1 over L and fy is equal to 0. The third delta function will be non-zero only when fx is equal to minus 1 over L and fy is equal to 0. And for all other values, these three delta functions will be equal to 0. Now let's calculate the product of the Fourier transform of the above field given in equation number 55, and with the multiplication of the transfer function of the Fresnel as given in equation number 53. So the product is listed in equation number 56 on the right hand side of that one. So each delta function has been multiplied by the corresponding transfer function. But you know that we are evaluating these individual quantities, these three individual delta functions, only at those points where those delta functions are non-zero. So for example, for the first delta function, in the first line we are using fx is equal to 0, fy is equal to 0, and the product will be evaluated at these two parameters. In the second row, we shall evaluate the second row at fx is equal to 1 over L and fy is equal to 0, and in the third row we shall evaluate the product at fx is equal to minus 1 over L and fy is equal to 0. So these are the three quantities you know that we have shown over here. So we shall put these values over here, but we shall not put these values on the delta functions, because if we put these values on the delta functions, then you know that the whole description, the whole physical meaning will be lost. But what we do is that we shall put these values of fx and fy only in the transfer function, on the transfer function parameters, which is e to the power minus iota pi lambda z, and within the parentheses we have fx square plus fy square. So we shall evaluate these this value of the transfer function, this expression of the transfer function on the given values of the fx and fy. So after substituting these one, we can write the equation 56. So we have written another equation 56 because both equations are similarly the same, but here is that we have substituted, we have evaluated the previous equation 56 with the values of fx and fy. Now you see that we have these terms, and now we want to calculate the inverse Fourier transform, because we have calculated the product of the two Fourier transforms, that is the Fourier transform of the input field multiplied by the transfer function, which is already in a Fourier transformed form, because both are operating at the frequency, Fourier frequency fx comma fy. And you know that we have evaluated equation number 54, the part which is lying within the curly bracket, and now we have to take the inverse Fourier transform of this quantity to get the field. So let's proceed further. So you see that in equation number 57 we have the field u of x comma y on the left hand side, and on the right hand side we have shown the inverse Fourier operator operating on each term. And you see that only it will operate on the terms which contains fx comma y, fy, that is the Fourier variables. So the inverse Fourier transform will operate on the Fourier variables in equation number 57. So after operating these one, we have shown the inverse Fourier transform of these three. So 58 shows the inverse Fourier transforms of delta of fx comma fy, which is equal to 1. That is a plane wave. It will give you a plane wave of unit amplitude, and normally incident plane wave will be obtained from the first Fourier transform, inverse Fourier transform in equation number 58, and from the second Fourier transform, if you take the inverse Fourier transform of the delta of fx minus 1 over L comma fy, you will get a plane wave e to the power iota 2 pi x over capital L. And in the third, which is shown in equation number 60, in equation number 60, if you take the inverse Fourier transform of delta of fx plus 1 over L comma fy, you will get e to the power minus iota 2 pi x over capital L. Thus finally the equation 57 reduces to the following form. So you see that substituting these computation of inverse Fourier transform in equation number 57, we come up with the end result as shown in equation number 61. So in equation number 61, we have the final result which represents the intensity calculation at the point x and at the point x comma y. So u of x comma y is given. So in the first step we have given the first row. In the second step we have combined the we have taken the common terms and we have combined the two terms in the summation form, so that we can convert them in the cosine function which is given in the last term. So you have u field in the last term according to 1 plus m into e to the power minus iota pi lambda z over L square multiplied by cos of 2 pi x over capital L. So you see that this is the field obtained from equation number 61. Now at z is equal to 0, if you put z is equal to 0 in equation number 61, you will see that the two planes zeta eta plane and the xy plane coincide, and the field u of x comma y is becomes equal to the input field. That is, the field at the point of observation becomes equal to the field at the input plane, which is obviously correct by putting z is equal to 0 in equation 61. Now the quantity of interest may be a physically measurable quantity is the intensity. So the intensity is given by I of x comma y is equal to u at x comma y multiplied by its complex conjugate. So you see that in the second row we have two brackets. One represents the value of u we have taken from equation number 61. The other represents the complex conjugate of that quantity. So multiplying the two, in the last the third row in equation number 62 gives the intensity expression. Now we want to get some useful meaning from this intensity expression. Let's analyze this intensity for different values of z. Case number 1. Let's evaluate the intensity when. You know that if you look at this one, we have the term over here, cos term, that has an argument pi lambda z over L square. So you see that this factor is very important because we want to get rid of this factor by putting some appropriate value of z. So because we want to get rid of this cos function, so that we can get some useful or meaningful results from equation 62. So you see that we are putting that quantity that I have explained previously. So pi lambda z over L square. So let's put that quantity is equal to 2n into pi. Or you can get the value of z from here, which becomes z is equal to 2n L square over lambda. So if you put that quantities over there, you know that the cosine function over there, that is this cosine function in the middle, that is cos of pi lambda z over L square will take its value, because you know that cos of, if you put cos that quantity is equal to 2n pi, so here the cos becomes equal to 1 for all values integer multiple of 2 pi, that cos becomes equal to 1. Because if you put n is equal to 0, you will get 0 and cos becomes equal to 2 pi over there. So for all integer values of n, that cos function, that is this cos function in the middle, will becomes equal to unity. So putting that 1, and we can now represent the intensity with a subscript of capital Z is equal to 2n L square over lambda, and the output is given on the right hand side of equation number 63, which is the square of 1 plus m into cos of 2 pi x over capital L. The intensity at the input plane can also be found from equation number 52, because the input intensity does not contain any, that complex variables, so we can directly take the square of that one to get the intensity. So this is the intensity in equation number 64, that is the input intensity at the input aperture at the grating. This is the input intensity, and equation number 63 is the intensity at the output plane. So look at these two expressions are the same, and these expressions are the same only for a value of z which is equal to 2n L square over lambda. So we can say that for integer values of n, the output intensity is the same as the input intensity, that is the replicas of the original object intensity repeat at the planes when z is equal to 2n L square over lambda. These replicas are referred to as the self images or the Talbot images. So you see that the self images or the Talbot images can only be produced from this equation, that is from equation number 62. If this equation is plugged in with this value of z, that is capital Z is equal to 2nl square over lambda, then equation number 62 will produce the same replicas as given by equation number 61. So the replicas generated by equation number 62 will be the same as equation number 61, but only at certain values of z which is satisfied by this equation, that is capital Z is equal to 2nl square over lambda for integer values of n only. And those images which are the same as the input images, that is the gratings, will be generated at these values of z. So these images are called self images or the Talbot images. Now let's discuss the case number 2, in which we are using the same value, the same parameter, but now that parameter we are going to set it equal to 2n plus 1 into pi. Before that we set that one equal to 2n pi, but now we are setting this parameter in case number 2 equal to 2n plus 1 into pi, or the z value will be equal to 2n plus 1 multiplied by L square over lambda. So now if you plug in this value of z or in the previous equation, that is in equation number 62, what you get is that you get a simplified expression as given in equation number 65. But you know that the only difference between equation number 65, the intensity obtained at the output plane using the value of capital Z is equal to 2n plus 1 multiplied by L square over lambda, this intensity differs from the intensity at the input plane, which is given in number 64 only with a negative sign. So here we have a positive sign with m, but there we have a negative sign with m. So these images are so you know that this differs from the original object intensity by a phase shift of a pi, that is contrast reversal images of the original object intensity repeat at the planes where we have z is equal to 2n plus 1 multiplied by L square over lambda. These contrast reversal replicas are also known as Talbot images. So you know that when you are using this value of z, that is z is equal to 2n plus 1 multiplied by L square lambda, you produce the same images as the input images but with contrast reversal. Now let's describe case number 3, where we are using the same parameter, but you know that here we are using this parameter, we are setting this parameter is equal to 2n minus 1 multiplied by pi by 2. Or we are getting z is equal to 2n minus 1 multiplied by L square over 2 lambda. So now if you plug in this value in equation number 61, in equation number 62, what you get is that you will get the after simplification you will get this result. So intensity evaluated, so intensity at the output plane evaluated at z is equal to 2n minus 1 multiplied by L square over 2 lambda, that is equal to the simplified result is given in the second row, which is equal to 1 plus m square over 2 within the parenthesis plus m square over 2 multiplied by cos of 4 pi x over L. So from here in the cos function you can see that the frequency is doubled with respect to the input field. In the input field you have the factor 2 pi. Now in this expression you have the factor 4 pi. It means that this will generate data that will have a sinusoidal function with a frequency twice that of the previous cases. The images represented by this output intensity have spatial frequency twice that of the original object intensity with much reduced contrast. So these replicas which occur at z is equal to 2n minus 1 into L square over 2 lambda are known as sub-Talbot images. So for this value of z we get images which are sub-Talbot images, and these sub-Talbot images are the images shown in gray for different values of n. So these images in gray for different values of m, for different values of n are shown. For example, n is equal to 1, the first one. For n is equal to the second gray function is shown. For n is equal to 3, the third one, and for n is equal to 4, we have shown the gray images. These gray images are the sub-Talbot images, and you can see here for these gray images the frequency is twice that of the frequency shown in the binary images, which are the actual images. So in the binary images, these are the input images, you know. or these are evaluated at the images which are shown at these values of z, that is 2n plus 1 into L square over lambda. And you see that here the z value is actually this one. So these the gray ones are the actual images, and the binary images are the actual images, and the blue and the gray one are the images which are the sub Talbot images. So look at this one. So you know that in the lower side of this figure you can see that we have used two values of z. Z is equal to 2n L square over lambda, and we have used this value for n is equal to 1, and then on the other side we have used this value for n is equal to 2. So these are the images which are the exact replicas of the original images. But you know that we have also in the lower side we have also used z is equal to 2n plus 1 into L square over lambda for n is equal to 1, and on the far end we have the same value for n is equal to 2. These images are the contrast reversal images. So the images are the contrast. For example, the binary image 1 and the binary image 3 are the exact replica of the original object, whereas the binary image number 2 and the binary image number 4 are the contrast reversal of the original objects. So on the binary images contain two sets. One are the original objects, and the second one are the contrast reversals. So the binary image number 1 and the binary image number 3 are the original replicas, and the binary image number 2 and the binary image number 4 are the contrast reversal images, whereas the gray images represent the images which are the sub-Talbot images with a spatial frequency twice that of the original spatial frequencies. So the Talbot images are shown for binary grating, whereas the sub-Talbot images are shown for sinusoidal gratings. So actually this is the end of slide number 45.